Okay, this is a quick video about converting between ocean graphs. What does that mean? Well, typically we want to look at x versus t, v versus t, and a versus t. So that's position, velocity, and acceleration. The one thing to know is that velocity, v, is the slope of x versus t. This is a definition. It is not something I can prove to you. We just say, if you know calculus, that v is dx dt. That is the slope. If you don't know calculus, you can think of this as rise over run. These are the same thing anyway. So whether you know calculus or not, it's rise over run. And of course, if you're calc savvy, you know that this is just the limit as delta t approaches 0. That's all a derivative is. So this is just your simple rise over run. Okay, how about acceleration? Acceleration has the exact same relationship to velocity that velocity has to slope. In other words, a is the slope of the v versus t graph. Another way to say that is a is delta v over delta t. If I tell you what a is, you can tell me how much v will change in a certain amount of time. So that's how you go from position to velocity and from velocity to acceleration. What if you want to go the other way? Well, it turns out that if the acceleration is the slope of velocity, then the change in velocity is the area under the VT graph. That may sound crazy to you, but one way to think of that is you say, well, the acceleration is delta V over delta T, but another way to say that is that delta V is A times delta T. And you may say, wait a minute, how is that the area? Well, if the acceleration is constant, then A times delta t is this area. And for those calc savvy of you, you might say, wait a minute, that's ridiculous. What if the acceleration is some weird curvy function? Okay, well, the whole point of calculus is that you just build lots and lots and lots of little rectangles, just like this one. And in the limit, as delta t approaches 0, the area under this is the sum of all those little rectangles, and it is still true. If you don't know calculus, you can just take it as a given that these will always be flat. And so it's just coincidental that delta V ends up being the area under the VT graph. And then likewise, if you know V and you want X, guess what? Exact same relationship. So you kind of go in a circle like this. If you have X and you want V, you go this way, you take the slope. If you have V and you want A, you take the slope, and then you go back down the ladder this way. I want to show you an example where we start with V. That way I can show you going both ways. Of course, if you understand this video, you should be able to be given this and get to this, or just start anywhere. So let's do one where you're given V. Typically in physics, you're not given a graph, you're given a story. So here's the story, let's turn it into a graph. This says a car speeds up from rest to 2 meters per second in 1 second. So they're talking about speed, and they're talking, so I should put that on my velocity graph. They don't give me a direction, so let's just call it the positive direction. Boom, that's it. I started at 0, I end at 2, and I did it in 1 second. So notice I fill this out as I read the story. The next piece says the car slows to rest in 1 second. Oops, sorry, it coasts for 1 second. The car coasts for 1 second. And so coasting, that just means you keep constant velocity for 1 second. Okay, then it says the car slows to rest in 1 second. So I just draw another straight line headed down. Okay, and then it says, then the car speeds up to 4 meters per second in the opposite direction in 1 second. Okay, so I just draw a slightly steeper line over there. Now, those of you, again, who are a little more savvy, you know some calculus, you may say, how do you know that it speeds up linearly? You are right. You got me. I absolutely don't know. But in the absence of other information, it's usually safe to assume that in these problems. The velocity certainly could curve to meet these, but then you're in the land of calculus, and then you actually have to be given a formula. You have to be given, like, how does it curve? It's some function. It's some function. And then those of you that know calculus, you know you're going to take derivatives and integrals and stuff anyway. That's not what this video is about. So we're just gonna assume they're all straight segments, okay? Okay, so the first thing I want to do is make my acceleration versus time graph. So we said that acceleration is the slope of v versus t. So the rise, in this first segment, I go from 0 to 2. So that's delta v over delta t is 2 minus 0 over 1 minus 0, okay? And then that gives 2. So the acceleration is 2. It is constant the whole time. How do I know that it's constant? the slope of a straight line is constant. Therefore, the acceleration is constant, at least over that interval. How about this next piece here? This next piece, the slope of this line is 0. It doesn't slope up or down, and so my next piece looks like this. Those of you, again, who are pretty mathy might say, hey, this doesn't make any sense. This is a discontinuous function, and that's unphysical. I couldn't agree more. The idea of this is to show you the concept of how in principle you would do this, and that's easier if I just have constant segments. Of course, in real life, this would curve down. There would be some weird curve here to connect them, and then we're back in the land of actually needing to know the functional dependence of that again. Now, you might say, you actually don't need to know the functional dependence. If you wanted to, you could make little rectangles. You could make little rectangles under that area and thus figure out the change in velocity. Boy, I've never argued with myself so much in a video before. I hope it's not distracting. Okay, anyway, we attack the next segment. This has a slope of -2. Why? It ends at 0. It begins at 2, and it goes from the span from t equals 3 to t equals 2. 3 minus 2. In other words, it has a slope of -2 because it decreases. So now I have the area as -2. And then finally, look, I'm going to have another negative slope. I go from 0 to 4, and it happens in 1 second. So I don't think you'll be surprised if I say that slope is -4. Okay, that's going in this direction. If you go in this direction, you want slopes. If you want to go in this direction, you want area. Okay, so area, what does that mean? The area under this first slice. Now, what you need to do is section these graphs into places where the behavior is consistent. In other words, I can't find the area of the whole of the entire graph. I mean, one could, but one finds the area of the entire graph by chopping it up into pieces: triangles, rectangles, positive triangles, negative rectangles, and so on. Okay, so this first piece is a triangle. It has a base of 1 and a height of 2. So the area is the base times the height divided by 2. So that's 1. So I have my x goes from 0 to 1. And notice it curves in order to get there. It is concave up. Concave up. It's concave up because the acceleration is the concavity of x. Okay, if you have positive acceleration, it's concave up. If you have negative acceleration, we'll see that later, you'll be concave down. Okay, so the next segment is this area. So this is 1 and this height is 2, so that area is 2. So that tells me how much I change by. Delta x is 2. I start at 1, I ought to go to 3. And I go there in a straight line. How do I know it's a straight line? The slope is constant. Velocity is the slope of position, and this has constant slope. Therefore, this must be a straight line down at the bottom. Okay, the next piece has a negative slope for velocity, but it still has positive area. In other words, just because my velocity starts decreasing, that doesn't mean I go the other way. I still have a positive velocity. I'm going to continue to move in the same direction, only now my acceleration's negative. So let's see, this area is 1 by 2, so that will be another 1. So I go from 3 to 4, and notice this time I am concave down. I'm concave down because I have negative acceleration. Notice also that at this point, the velocity is 0. Notice here that at this point, my graph is flat. The slope at that point is 0. And that's significant because this is a turnaround point. This is a maximum. This is where it goes from moving in the positive direction to moving in the negative direction, because that's what the velocity says. When the velocity is positive, you move in the positive direction. When the velocity is negative, you move in the negative direction. Okie doke, this last slice we need to look at is this triangle. Now, the thing to watch out for is that this triangle has a base of 1 and a height of -4, not +4, -4. That means that the area of this triangle is -2. So now I have delta x equals -2, meaning if I start at 4, I ought to lose 2. So I end at 2. Notice this is concave down because I have negative acceleration again. Okay, so this is just one example. Hopefully, you see that this process is easier when you break it into lots and lots of little tiny steps. You cannot do these problems in one bite. You have to break them into chunks where the behavior changes. Okay, hopefully this was more helpful than confusing.